Welcome to clickmyproject.com. Now we will discuss about the product for area efficient parallel FAR digital filter structure for symmetric convolution based fast FAR algorithm. Next we will see the abstract for the product. Due to the explosive growth of multimedia application, the dependent of high performance and low power digital signal processing is getting the higher and higher processing. Finite impulse response digital filters are one of the most wide used in the fundamental device performed in DSP system, ranging from wireless communication to video and image processing applications. Based on the fast finite impulse response algorithm, this paper proposes a new parallel FER filter architecture, which are the benefits to systematic coefficients in terms of the hardware cost under the condition that are the number of taps in the multiple of 2 or 3. The proposed parallel FER filter architecture explored the inherent nature of systematic coefficient, reducing the half number of multipliers in sub-filter section at the expense of the additional adder in pre-processing and post-processing blocks. Exchanging the multipliers and adders in the advantage because the adder weightless than the multiplier in terms of the silicon area. In addition, overall head up from the addition adders in pre-processing and post-processing blocks stay fixed and do not increase along the length of the FER filter architecture, whereas the number of reduced multiplier increased along the length of the FER filter architecture in the proposed architecture. Overall, the proposed parallel FER filter architecture can lead the significant hardware saving the systematic convolution from the existing FFA parallel FER filter architecture, especially when the length of the filter is large. Then we will see the flow diagram for the product, the input samples and the error samples to apply the delay unit architectures. The delay unit architecture is mainly based on the register element. The deflip register elements to use the delay adder process. Then the delay element result is applied to the partial border generation unit. The error bit samples is to create the error coefficient manner. Thus, add the addition work to the error input bit samples using the partial border generation architecture. The partial border generation addition architectures mainly based on the carry select addition process. Then to apply the shift add architecture block. The partial border generation result is to pass the shift add architecture block. The shift add architecture block is used to the addition the partial border generation results in separate manner. This process is mainly used to the reduce the carry propagation time and to reduce the hardware complexity for the shift add architecture work. Then the shift add architecture result is applied to the delay and adder element. The delay and adder element mainly used for the store the results in register, then to apply the final output results. The final output results to get the delay and adder element. The delay element is mainly used for the deflip register element. The adder element is mainly focused by the LSB and MSB position for the shift add architecture result and to apply the delay and adder unit elements. The final output samples is mainly based on the synthesis and simulation results elements. The simulation results is mainly passed by the binary results element, and the synthesis report is mainly focused by the satisfy the parameter results for the in our architecture. And finally we see the output for the product. First of all, we open our processing folder, then we open the Xilinx ISC project. Our program is developed in VHDL language. Then we select the waiter update block to select the simulation work, then to select simulate behavioral model. We run the process for our processing result, then open the Xilinx ISM projects. The simulation behavior model was completed successfully. Then create the ISM project list. Then we apply the binary input and to calculate the output weighted bits. Now apply the 16-bit data length for our project. Then add the error signal in coefficient manner. Then apply the clock pulse. We can create the programmable process. Just we close the simulation process. Next we go into this implementation work. The implementation work to create the view RTL schematic. Just we run the schematic diagram. The RTL schematic diagram is mainly used to create the RTL diagrammatic representation. Just we double click this diagrammatic representation is mainly used to what are the logical blocks is placed in our weighted filter architecture. Then the technology diagram is represents the what are the lookup table and input output buffers, then wire connections and flip-flop pairs to be applied by the our overall weighted filter architecture. Then we go to the design summary result. Then the synthesis report. Just we generate the synthesis report for the weighted filter architecture. This architecture results is to calculate the area of the device utilization of weighted filter architecture, and finally we calculate the timing allocations for the latency and delay time calculation for our weighted filter architecture level.